Wait! Greetings, peeps! I'd like to discuss the first fundamental quantity of nature, and that would be length. Length is pretty simple, but we're gonna define it a little bit more precisely in terms of something known as distance and displacement. First, distance. Distance is a scalar measurement of length. A scalar is just something that measures magnitude only. Magnitude being the amount. That's all it is. Magnitude is a cool word meaning amount. Okay, so the amount of the length. The examples of distance are the tree is 20 meters tall. The distance of that tree is 20 meters. That's its distance, pretty much from the ground to its crest or canopy. The bike ride covered a total distance of 7 kilometers. Again, we're not concerned about anything but the amount of length, and that would be distance. Whereas displacement is a vector measurement of length. Vector means magnitude and direction. If you've seen the movie Despicable Me, the animated feature, there's a villain called Vector, and he's kind of like the up-and-coming villain. And he's made up of magnitude and direction. Oh yeah! Example, the car moved 2 kilometers north. Notice that in this case we have the magnitude, the amount, 2 kilometers, and a direction. In this case it could be specified as north. Displacement is the change in position relative to a coordinate system. And a coordinate system can be as simple as a one-dimensional line, like a number line, or it could be maybe a two-dimensional grid, like an XY axis, or 3 dimensions, X, Y, and Z. In this case, in 1 dimension, we consider it mathematically to be represented like this. Delta X, this triangle refers to the Greek letter delta, which means change in. So the change in X equals the final position of X, just X, wherever it ended up, minus X naught. This little 0 over here means not, or you can consider it to be X original, okay? So X final minus X original, that's the change in position, delta X. That's displacement. Here's an example of movement along a simple one-dimensional coordinate system. Okay, over here we have our coordinate system. It's basically a number line going from an origin at the center to positive X, which I've just designated arbitrarily as east, and we have the negative X direction this way, which would be designated west, travel in the west direction. Okay, so here's how the motion's gonna go. We're going to take displacements, change in position, relative to the previous position. So for example, we're gonna start at the origin. It's a nice place to start. And we're gonna move 2 meters in the positive direction. Then from wherever we are, we're going to move -3 meters. So we're gonna move 3 meters in the backwards direction, negative direction, which would be west. Then from that position, we're gonna move 4 meters forward and another meter forward. So a couple things we wanna figure out is where are we and how much distance did we actually cover? Okay, well I've done this graphically so that you can see what's going on. We have 2 meters here from 0 to 2, so we're at position A. Okay? Then we were told to go 3 meters back, we're at position B. So if I go 3 meters back, notice that this arrow is pointing in the negative direction. Okay, that's a negative vector. Vectors can be represented as arrows with the magnitude being representative of the length. Okay, so for example, this 2 meters here is shorter than the 3 meters here. Even though this is negative, it's just, all it means is pointing backwards. So this vector is smaller than this one. So if we move 3 meters back, we're at position B, which is -1 relative to the origin. Okay, then we were told that we're gonna go 4 meters in the positive direction. So from here, we go 4 meters forward, and we end up at position C, which is 3 meters east of the origin. Okay, 3 meters in the positive direction relative to the origin. And then we go 1 more meter forward, so we end up at position D. This is our final place, 4 meters away from the origin. Even though we did go into negative territory a little bit, we end up in positive zone, which is at 4 meters. Okay, so the final position relative to the origin was 4 meters by going back and forth here along the coordinate system, positive and negative. But the total distance traveled was 10 meters. Well, how did we do that? Well, we went 2 meters forward, 3 meters backwards. That's 5 meters in total. 4 meters of travel would be 5 plus 4, 9, and then another one is 10. So we just add up the absolute value of all of these distances. You take the absolute value of all of them, all of these numbers, and that gives you the total distance. Whereas if you're looking for position relative to the origin, you add the numbers up, including their sign. Okay, we're gonna do the same exercise with this same coordinate system, except we're gonna change this coming up, where the displacements are relative to not the previous position, but the origin, and you'll see how the dynamic changes a little bit. Okay, same coordinate system, but now we're going to look at motion where the displacement of that motion is relative to the origin. So the change of position now is specified relative to the origin, so it's subtly different. We have the same numbers here, but we'll see that the pattern is a little bit different. What this means is that we're going to go to position 2 relative to the origin. So that's the same as last time. We go to position A, and that's where it was before. Now with B, we're going to go to position -3 relative to the origin, which means we go all the way back here. So B is now at position -3. How far do we travel from position A at 2 meters? -5 to get to this point over here, okay, where B is. C is at position 4 meters. So we're going to go all the way from position B at -3 to position C at 4 meters. That's a displacement of +7 meters. So we're going to go 7 meters in the positive direction to the east. So we go crisscrossing through the origin, as you can see here, with this switch of positive and negative, right? Now we go backwards again. Even though this is positive, check it out. We're going to go from position 4 to position 1, which is relative to the origin. So at position 4, that's C, we go backwards 1, 2, 3. Here we go, here's the vector, to position D. So what we can see very readily is that our final position is so easy to detect relative to the origin because it's specified right here. You just look at D, okay? Position D is 1 meter. That's where we end up. And we started at position 0. So our total displacement, or final position relative to origin, final position relative to origin is just 1 meter, +1 meter, okay? What is the total distance traveled? Well, notice that even though we have these same numbers before, because we go crisscrossing through the origin, it's much larger than before. It was 10 meters in the last look at motion. Now it's 17 meters. So check this out. How do we get the 17? Again, same technique. You just add up all of the magnitudes of the vectors, absolute value of them. 2 plus 5 is 7, plus 7 is 14, plus 3 is 17. So remember, you take the absolute values, ignore the negatives, just add up that column, and that's the distance traveled. And that's what it is. 2 number lines with specifying displacements relative to position, previous position, and relative to origin. Thank you, Morad, out.